Yes, dear students, so today let us study about the topic isomerism in coordination compounds. In the last class, we have studied about the stereochemistry of the coordination compounds and the effective atomic number. The compounds having the same molecular formula but different structures and hence different physical and chemical properties are called isomers, and the phenomenon is known as isomerism. Coordination compounds give rise to a wide variety of isomers due to different types of linkages and different structural arrangement of the ligands around the central metal ion. These isomers are broadly classified into two categories. Number one, structural isomerism, and number two, stereoisomerism. Structural isomers, they differ in the structures, and stereoisomers, they differ in the spatial arrangement of the ligands. In structural isomerism, the examples are ionization isomerism, hydrate isomerism, linkage isomerism, coordination isomerism, and coordination position isomerism. The stereoisomerism contains geometrical isomerism and optical isomerism. Now let us restrict our study only to these structural isomerism. Coming to the first one, ionization isomerism. Complexes having the same molecular formula but are produced by the interchange of the positions of the ligands inside and outside the coordination sphere, so that they give different ions in solution on ionization, are called ionization isomers, and the phenomenon is known as ionization isomerism. Coming to the examples of this kind, the pentamine bromo cobalt 3 sulfate, which is reddish to violet in color, on solution gives pentamine bromo cobalt 3 ion and the sulfate ion. This complex gives a white precipitate of barium sulfate with barium chloride solution, showing that the presence of sulfate ions in the solution. However, this complex is not going to give pale yellow precipitate of silver bromide with AgNO3 solution, because the bromide is linked directly to the cobalt through a coordination bond or coordinate bond. Therefore, the ions which are present in the coordination sphere, they are not going to ionize. Suppose if I take the another isomer of this complex is pentamine sulfato cobalt 3 bromide, which is red in color. This compound on ionization gives pentamine sulfato cobalt 3 ion and bromide ion in solution. Therefore, this complex gives pale yellow precipitate with AgNO3 solution, and it is not going to give any precipitate with barium chloride solution. The other examples of this type are the tetramine Dichloro cobalt 3 nitrite and the tetramine nitrito N chloro cobalt 3 chloride. In the earlier case, it gives a test for nitrite ion in the solution because it is present outside the coordination sphere, and in the second case, it gives a test for chloride ion, that is also for chloride ion of 1 mole. The other example is tetramine dichloro platinum 4 bromide, and another example is tetramine dibromo platinum 4 chloride. The earlier complex gives a pale yellow precipitate with AgNO3 corresponding to the presence of the bromide ions in the solution. The second complex gives a white curdy precipitate with AgNO3 showing the presence of chloride ions in the solution. Because the earlier complex contains bromide outside the coordination sphere and the second complex contains chloride outside the coordination sphere. Now let us take the another, that is hydrate isomerism. Complexes having the same molecular formula but are produced by the interchange of the positions of the water molecule inside and outside the coordination sphere are called hydrate isomers, and the phenomenon is known as hydrate isomerism. Sometimes it is also called solvent isomerism also. This hydrate isomerism is similar to ionization isomerism. Now, let us take an example. Hexa aqua chromium 3 chloride, which is violet in color. In solution, it gives the 3 chloride ions, and when it is treated with the AgNO3, we get the AgCl precipitate corresponding to 3 chloride ions, and this compound will not lose water when it is treated with concentrated sulfuric acid. It means concentrated sulfuric acid absorbs the water which is present outside the coordination sphere, and this water is also called water of hydration. However, concentrated sulfuric acid cannot take the water molecule that is attached to the central metal ion, or it is also called coordinated water. The coordinated water cannot be taken by concentrated sulfuric acid. Let us take another example of the same isomer, that is penta aqua chloro chromium 3 chloride monohydrate. This in solution gives the pentamine chloro chromium 3 ion, 2 chloride ion and a water molecule. Therefore, this compound gives the silver chloride precipitate with AgNO3 corresponding to 2 chloride ions. However, it loses 1 water molecule when treated with concentrated sulfuric acid, because that water is the hydrated water. The third example is the Tetra aqua dichloro chromium 3 chloride dihydrate. This in solution gives Tetra aqua dichloro chromium 3 ion, chloride ion and 2 water molecules. So this complex gives the white precipitate with AgNO3 corresponding to 1 chloride ion, and the concentrated sulfuric acid absorbs the water corresponding to 2 water molecules with concentrated sulfuric acid. This shows that the concentrated sulfuric acid can take only the water molecules which are present outside the coordination sphere. Let us take the other examples of this type are the Aqua, Chloro, Bisethylene diamine, cobalt 3 chloride, and another one Dichloro, Bisethylene diamine, cobalt 3 chloride monohydrate. The earlier complex will not give any water molecule, whereas the next complex, it gives one water molecule with concentrated sulfuric acid. Coming to the next isomerism, that is called the linkage isomerism. In some ligands, there are two atoms which can donate their lone pairs. Example, nitrito N ion, written as NO2 minus ion. Here, nitrogen of the nitro group may donate, or oxygen of nitro group may donate a lone pair of electrons to central metal ion. If nitrogen donates a lone pair of electron, then that ligand is called nitrito N. If oxygen of the nitro group is going to donate the electron, then that ligand is called nitrito O ligand. Complexes having the same molecular formula but differ in the atom of the ligand which donates a lone pair of electron to the central metal ion are called linkage isomers, and the phenomenon is known as linkage isomerism. I have given below an example, that is pentamine nitrito N cobalt 3 chloride. In this case, the nitrogen of the nitro group donates a lone pair of electron to the central metal ion, that is cobalt 3 ion. In the second case, it is called the pentamine nitrito O cobalt 3 chloride. Here, oxygen of the nitro group donates a lone pair of electron to cobalt 3 ion. Other ligands which give rise to a linkage isomerism. Other ligands which give rise to linkage isomerism are the cyanoligand and isocyanoligand. The next, thiocyanato and isothiocyanato ligands. Co-ordination isomerism. Complexes having the same molecular formula but the attachment of the ligands to the central metal ion is different are called coordination isomers, and the phenomenon is known as coordination isomerism. This type of isomerism is found in case of the compounds having both cationic and anionic complexes. Let us take an example. The first one is hexamine cobalt 3 hexacyanochromate 3. In this case, the 6 amino groups are attached to the cobalt 3 ion and 6 cyanide groups are attached to chromium 3 ion. The isomer of this is the hexamine chromium 3 and hexacyanocobaltate 3. In this case, the 6 ammonia ligands are attached to chromium 3 ion and the 6 cyanide ligands are attached to cobalt 3 ion. The second example of this category is tetramine copper 2 tetrachloroplatinate 2 and tetramine platinum 2, tetrachlorocuprate 2. In the third example, that is hexamine chromium 3, hexacyanochromate 3 and tetramine dicyanochromium 3, diamine tetracyanochromate 3. In this case, both cationic and anionic complex have the same central metal ion, but the arrangement of the ligands is different. This is also an example for coordination isomerism. Coming to the last one, coordination position isomerism. Complexes having the same molecular formula but the position of attachment of the ligands to the central metal ion is different are called coordination position isomers, and the phenomenon is known as coordination position isomerism. This type of isomerism is found in case of bridged complexes. Given an example here. So the first one is the dimehydroxo hexamine dichloro dicobalt 2. So in this bridged complex, the first cobalt is attached to 4 ammonia molecules and the second bridged cobalt ion is attached to 2 ammonia and 2 chloro ligands. The complex, the arrangement of the ligands attached to the central metal ion is different, whereas the bridging groups are the same. Here, the 3 ammonia and 1 chloro groups are attached to 1 cobalt, and 3 ammonia and 1 chloro is attached to another cobalt. So here the attachment of the ligands in both the central metal ions are different. So this becomes an example for coordination position isomerism. Students, let us study the geometrical isomerism in the next class. Before that, just here I have shown a diagram of isomerism in coordination compounds, so which I have already explained. Here I have shown the ionization isomerism and the various examples for these ionization isomerism. Here it is a solvent isomerism or hydrate isomerism. So this table gives initially the chromium complex, all the water molecules are inside the coordination sphere. So therefore they will not give any water molecules. But in the second case, one water molecule is outside the coordination sphere, so that can be easily removed. In the third case, the 2 water molecules are outside the coordination sphere, so those 2 water molecules can be easily removed. Now the water molecules which are outside the coordination sphere, so they come out from the compounds at a temperature of 102 to 105 degrees centigrade. The water molecules which are inside the coordination sphere, they come out from the complex at a temperature of around 115 to 118 degrees centigrade. Here I have shown the various other complexes and their isomerism. Shown the linkage isomerism, coordination isomerism, coordination position isomerism, and so on. Students, go through the isomers which are important as far as the examination point of view.